네, 오늘 벌써 2023 H2 미트 컨퍼런스 행사의 마지막 날이 되었는데요. 마지막 날까지 테크토크에 많은 관심과 애정으로 함께해 주시는 여러분 대단히 고맙습니다. 인사드리겠습니다. 안녕하십니까? 저는 오늘 행사의 사회를 맡은 아나운서 김지영입니다. 반갑습니다. 네, 그럼 지금부터 H2 미트 컨퍼런스 2023 테크토크의 마지막 세션인 토픽 4를 시작하도록 하겠습니다. H2 Storage and Distribution이라는 주제로 진행이 되는 토픽 4에서는요, 총 5개의 강연이 준비되어 있고요. 각 20분씩 11시 40분까지 진행이 될 예정입니다. 혹시 질문이 있으신 분께서는 각 강연이 끝난 후 질의응답 시간을 이용해 주시기 바랍니다. 네, 그럼 먼저 첫 번째 강연을 소개해 드리겠습니다. CSIRO 연방과학산업연구기구의 Senior Principal Research Scientist이신 살브 기디님께서 강연을 준비해 주셨는데요. 제목은 Technologies for Renewable Liquid Fuels for Transport of Hydrogen입니다. 네, 그럼 연사분을 무대 위로 모시겠습니다. Dr. Sarbjit, please come forward to the podium. 네, 여러분 따뜻한 환영의 박수 부탁드립니다.
Thank you. Welcome everyone attending this session of the conference. Just a bit of my introduction. My name is Giddey. I'm the group leader in one of the energy business unit of CSIRO, and I'm going to present the technologies for the renewable fuels actually, which we can basically make from renewable energy sources, and looking at how hydrogen produced from renewable electricity can be used to make these liquid fuels, which can be used for the transport of renewable energy into other countries, and also for local utilization. I will also touch base on some brief introduction of CSIRO and also the work which is being done in CSIRO on the hydrogen related technologies. So CSIRO is Australia's major government funded research and development organization, and we have about 5,000 staff, and we have about $1.2 billion budget. So about half of the funds come from the government, and rest of the funds for the R&D work comes from by working with the industry and through our intellectual property, through licensing our technologies. Yeah, and just a bit on CSR's, some of the inventions I have just listed here. As everybody knows about Wi-Fi that you use every day for your laptops and for your mobile phones. So it's CSIRO's own invention, and also the plastic banknotes, that's also CSIRO's invention, and some of the others. Just to mention ultra battery, that was also invention of CSIRO, which is a hybrid technology of lead acid and ultra and supercapacitor. So here, this is just showing the complete suite of hydrogen related technologies, just from starting from hydrogen production by biomass or by electrolyzers integrated with the renewable energy sources, or up to the end, utilization of that hydrogen in the industrial sector or for automotive applications. So CSIRO is working and developing on various technology in this suite of technology shown here. So just on the group's activities, so within CSIRO Energy Business Unit, we have about 350 staff, and Energy Business Unit is then further divided into 3 programs, and one of the programs is Energy Technologies. And within that energy technologies, we have 3 groups, and one of the groups is thermal electrochemical technologies, and in that group most of the work is related to hydrogen. and renewable fuels, and another group which is working on solar related technologies like solar PV and solar thermal, and the third group is working on sustainable carbon technologies, mainly looking at CO2 capture and CO2 utilization. Within the group thermal electrochemical technologies, we are basically focusing on 4 areas. The first one is on the production and utilization of renewable fuels, such as hydrogen and ammonia. So developing those technologies which are more efficient, more scalable, and can be also deployed at distributed scale. Some of the technologies we are looking at are the fuel cells, electrolyzers, hydrogen storage, and also hydrogen utilization and ammonia utilization in solid oxide fuel cells or in the PEM fuel cells. The next area we look at is circular economy aspects of these technologies. As you know that these technologies use quite expensive material which can be very scarce for example, using all the noble metal materials, palladium, platinum, iridium, we are developing those technologies, how these devices can be recycled in terms of also extending their lifetime, but also looking at how we can take out the materials and use them again, to develop, to build those devices again. The third area we look at is the techno-economic analysis, CO2 footprint and life cycle analysis. As you know, that several technologies are being proposed, put forward for reducing the CO2, but also looking at how these technologies can really make sense in terms of their scalability, technical viability, and so this is something one of the teams is dedicated to doing that work, looking at techno-economic analysis, to see how viable are those technologies before we really start into delving into the major deployment or scale of those technologies. The last bit is on looking at how these technologies, which are again based on hydrogen, ammonia production, utilization, how these technologies work together. So as you know, not a single technology can be used for any application. It has to be looking at some hybridizing of these technologies to make them more efficient, more economical, and also meet the demand, which is being put by vessel, whether it's the automotive sector or the industrial processes. So that's the work which we do, looking at how. So we have established a Center for Urban Energy Systems in CSIRO in Melbourne. That's where we look at, it's a kilowatt class facility. We have 20 kilowatt solar PV where we can generate hydrogen and then store hydrogen and also utilize it and see how these technologies work together by putting some simulating load cycles, whether it's the automotive load or industrial processes load or it's a residential load. So our labs are situated in Victoria, in Melbourne, and in Newcastle, in New South Wales, and in Brisbane. That's where most of the work on hydrogen and ammonia-related technologies is carried out. So this is just to show Australia's renewable energy potential. As everybody knows, so Australia has vast resources of renewable sources. Whether it's a solar PV, wind, or geothermal, tidal power, and if we look at Australia's current electricity installed capacity is around 65 gigawatt, and if we compare that with the global installed capacity, it's only around 8,000 gigawatt. And Australia has a renewable energy potential of more than 25,000 gigawatts. So you can see that how much capacity Australia has to turn those renewables into some usable form, or for example liquid fuels, which can be transported over long distances to places where the renewable energy source is not available. So this is another map, which shows Australia's renewable hydrogen mapping scenario. As you can see that, in the map, the dark green patches, in the inland places, so those are the places where both solar and wind both are available. So that means you can look at very, very high capacity factors, more than 70%. And where one of these resources is not available, there's a hydroelectric power available. So that means, we can put these together, achieve very, very high capacity factors, and then use that electricity to produce hydrogen. As you know, the cost of hydrogen is dependent upon major three factors. One is the electrolyzer cost itself, electricity cost, and also the capacity factor, how long you can run your electrolyzer during the day. So these are the three factors, which really are going to determine the cost of hydrogen. So Australia is in a very good place, to really look at using electrolyzers and using renewables and produce hydrogen, and turning that into liquid fuels. On the right hand side, that's the pie chart, which basically shows the kilometer square of land area of top fifth of the prospectivity ratings. As you can see that, it's a lot of land available where the renewables are available to very, very high capacity. The fuels under consideration are three fuels, actually, three types of liquid fuels. So one is liquefied hydrogen, and the second one is ammonia, and then third is methyl cyclohexene. As we know that all of these have their own advantages and disadvantages. Liquefied hydrogen, it requires energy input there, almost 1/3 of the energy content of hydrogen. And but it's pretty good fuel. It's just on-site available. Pure hydrogen is available. You can immediately use it. But on the other hand, liquefied hydrogen, there's no infrastructure yet to transport it from one place to the other. And also, actually, there are some boil-off losses as well. So these are the things which we have to consider, while considering liquefied hydrogen as a transportable fuel. The second one is ammonia, and ammonia, as you know, it has a highest hydrogen content in there, and there's already infrastructure to transport ammonia from one place to the other. All the regulations are in place, but as you know, ammonia still requires energy to produce it and also crack it. Not only that, once you crack it, you have to really purify that hydrogen so that no ammonia is left in there to use it for the fuel cell applications, whether it's residential or automotive applications. And on third one is methyl cyclohexene. That's basically, you use methyl cyclohexene as a way of carrying hydrogen from one place to the other. So that means, you have to hydrogenate toluene to convert into methyl cyclohexene, and then again convert methyl cyclohexene into toluene. Both processes require higher temperatures, higher pressures, and as well as some purification will be required when you dehydrogenate methyl cyclohexene into hydrogen. And another disadvantage is that we have to, once methyl cyclohexene is transported, and then you strip hydrogen out, and you have to send back that toluene actually in the ship. So that's going to cost. Apart from liquefied hydrogen, ammonia, and methyl cyclohexene, there are other fuels also being considered, like methanol, dimethyl ether, even methane as well. If the CO2 can be captured from some sources, from industrial processes, so we can convert that CO2 and hydrogen produced by electrolyzer into these liquid fuels. So I'm just going to cover some of the technologies being developed. So there are conventional technologies, and then there are new technologies being developed to make ammonia production and methyl cyclohexene production more at a distributed scale, make it more efficient, and also, generate some processes which can be integrated easily to the renewable energy sources. So this slide basically shows, how ammonia synthesis technologies are being developed. As you know, currently ammonia is produced by Haber-Bosch process. Natural gas is the feedstock in there used, and it requires very high temperatures and pressures. So we are looking at more than 200 bar pressure. So here actually these are some of the alternatives people are looking at. So one is just improving the Haber-Bosch process itself. So more about, developing new catalysts, improving the catalysts and absorbents which can absorb ammonia, and then basically, shift the equilibrium, so you can produce more ammonia, more conversion of nitrogen hydrogen to ammonia. And then the second one is looking at, just producing hydrogen from electrolyzer, and then you compress that hydrogen into to higher pressure, and also produce nitrogen from air separation unit, and then you can use still Haber-Bosch process and produce ammonia. The third one is on the a metal membrane process. So this is the technology which there are a couple of institutes working on. We are also working on that technology that's based on hydrogen permeating membranes. So when hydrogen permeates the membrane, it's very, very reactive. So basically on the other side, you can have nitrogen in the presence of catalyst to produce ammonia. The other technology which people are looking at is also plasma assisted catalysis, electrocatalysis. As you know, breaking the nitrogen bond is very, very difficult. And so we can have plasma which can assist you to convert that nitrogen into NOx species, and then those NOx species can be then electrochemically converted easily into ammonia. So that's another technology. And the last one is the electrochemical synthesis of ammonia, and that's basically based on aqueous, polymer, or ceramic membranes. So that's the process. Basically, we call it as a holy grail technology. If it can be developed, just a one single reactor, you just supply water or steam and nitrogen, and you can produce ammonia. But it's low temperature processes, very, very slow kinetics. And on the right hand side, I have shown, the current ammonia synthesis rates are 2 to 3 orders of magnitude low actually still. So a lot of work is required in that area. Okay, so this is just a slide that is showing how ammonia can be used for different applications, different options. You can electrochemically oxidize ammonia. That's one of the technologies being developed. So you can just produce hydrogen and nitrogen. And the other one is you can use ammonia, you can crack it and purify hydrogen, and then you compress it for automotive applications in the fuel cell vehicles. The third one is for residential applications. You just crack ammonia, produce pure hydrogen, and use it in the PEM fuel cell. It doesn't require any compression in there, and that can be used for distributed power generation applications. The next one is that ammonia can be directly utilized also in solid oxide fuel cell. That allows ammonia to be in situ cracked, and you do not have to crack it outside, and you can produce power. The last one is also ammonia can be used in the internal combustion engine. So that's another technology which is being looked at, and for mainly for marine and locomotive applications. So on methyl cyclohexane, so the conventional process is basically, you can have hydrogen produced by electrolyzer, and then you can use a hydrogenation. You can do hydrogenation of toluene, and that requires around 200 degrees centigrade temperature, and that's an exothermic process. And then to dehydrogenate, you need 350 degrees centigrade temperature or so, and 30 bar pressure, and that's an endothermic reaction. So once you produce hydrogen, it has to be then purified as well. And there are some of the examples on the right hand side. That's pretty well known process which Chiyoda has demonstrated, by shipping methyl cyclohexane from Brunei to Japan. That's what was done in 2022. So now we are looking at, can we look at some electrochemical technology, why we want to look at electrochemical technology, because they can allow us to be easily integrated with the renewable energy sources, and they can be at a distributed scale. And also, if we are using a membrane in there, ceramic membrane or polymer membrane, that will allow us to produce pure hydrogen. It may not need any hydrogen purification. So that's the processes. So these electrochemical, so one at the top, that's a electrochemical process, but then at the bottom, that's a metal membrane, for example, base process. So both, either it can be voltage driven, and the bottom one based on the metal membranes, that can be just a pressure driven process. But again, these technology very early stage. There's a lot of work being done in this area. And so in order to do the hydrogenation and dehydrogenation, you need some electrolyte materials actually. So here actually I have just shown some of the materials that can be used. It can be ceramic based materials, for example, barium cerate based materials, and they can allow you to conduct protons. And the advantage of developing these electrolyte materials is that they work around 350 to 400 degrees centigrade temperature, but it's very challenging because the electrolyte materials are, it's a low proton conductivity, but also not that robust in nature. But this can be the next thing which probably can make our dehydrogenation processes quite efficient if we can develop those materials, and it can be deployed to not only for methyl cyclohexene or toluene, it can be also used for ammonia cracking or ammonia production as well, because you can just have, for example, you can have steam on one side, you produce your protons which goes through the other side, and you can have hydrogen on the other side. So this is a currently there are no materials which are available which can give you sufficient proton conductivity but are also robust, so that's something which is quite good area to look at. So I just want to give you some examples where our group has been able to develop some technologies, also have been able to spin up some companies. So one on the top, that's based on, that's Endova. That was about 2 years ago. We spun off that company. That's based on our PEM electrolyzer technology. And the company is looking at developing 2200 kilowatt power generation systems for off-grid remote area power applications, and we have main Sequence Venture and Ample as our partners. So Ample is a main diesel supplying company. They have about 80,000 customers in Australia, and they are looking at deploying hydrogen-based systems, basically replacing the diesel generators with those hydrogen-based systems. The next one is the Hoyeon Energy. This is a recently spun-off company which has been formed based on CSIRO solid oxide electrolysis technology, and that technology is based on our tubular cell geometry rather than planar geometry. And we have BlueScope Steel and RFC Embryon as our partners. So as you know, this technology works at quite high temperature, about 800 degrees centigrade temperatures, but the advantage is that you can embed a lot of low cost thermal heat from the industrial processes, like from steel making or from ammonia production, and that allows you to reduce the electricity input in the process by 30%. So as for example, if a low temperature electrolyzer, you need about 55 to 60 kilowatt hour per kilogram of hydrogen production. With this technology, you will need around 40 or 35 kilowatt hour per kilogram of hydrogen. So that's the advantage of that technology. And just a bit touching on the ammonia synthesis, this is another technology which we have been developing. As I mentioned, it's a membrane-based technology, and it allows you to use hydrogen directly from electrolyzer and can be fed to our reactor. It's a hybrid concept, membrane-based reactor, and you can produce ammonia. And we have been able to produce ammonia at 450 degrees centigrade temperature and around 30 bar pressure. The hydrogen, which is basically available from electrolyzer, feed it directly to the electrolyzer, we are able to have between 10 to 15% hydrogen to ammonia conversion rates. So that's another technology. It's based on our metal membrane. Again, it's ammonia cracking technology, and this technology allows you again to produce 100% pure hydrogen. So we demonstrated this technology in 2018, and that was by refueling Hyundai's and Toyota's fuel cell cars. Yeah, I will finish here, and we have been working with Hyundai on to develop this technology to next stage. Currently, we are at 40 kilograms hydrogen production per day. Thank you.
Much for your presentation. 네, 큰 박수 부탁드립니다. Now, I'd like to ask participants if they have any questions, so please wait for a moment. 네, 혹시 질문이 있으신 분께서는 자리에서 손을 들어주시면 마이크를 전달해 드리도록 하겠습니다. 네, 질문이 없으시면 다음으로 진행하도록 하겠습니다. Thank you, Dr. Sarbjit. Please return to your seat.
Thank you.
네, 그럼 다음으로 헤레우스 구 한국 첨단 소재의 글로벌 헤드 오브 세일즈 헤테로제니어스 카탈리시스이시자 또 바이스 프레지던트이신 도미닉 스페르젤 님께서 강연을 해 주시겠습니다. Catalytic challenges from HC2 production to NH3 transport and fuel cell applications. Precious metals catalysis as key enabler for the hydrogen economy. 라는 제목의 강연을 청해 듣도록 하겠습니다. Mr. Dominik Sperzel, please come up to the stage. 네, 여러분 큰 박수로 환영해 주시기 바랍니다.
Good morning, everyone. I hope you can hear me right okay. My name is Dominik. I'm Global Head of Sales for Heterogeneous Catalysis within the Heraeus company. And today it's my pleasure to introduce a little bit the world of precious metal catalyst. So precious metal, very fancy material, ultimately where our company is specialized in. And I'm accompanied today by my Korean colleagues from Heraeus Korea and our local partner, Korea Advanced Materials. Yeah, precious metals are precious metals are all around us, and also within the hydrogen economy, they are all around us. So they are used within the generation of hydrogen, they are used within the distribution and transport, and they are also used on the application side. And when we talk about precious metals, we normally think about metals like iridium, platinum, ruthenium, palladium, and also rhodium. And today I brought a few application examples for you. So I will talk a little bit about catalysts for PEM electrolysis. I will talk a little bit about deoxygenation catalyst for the purification of hydrogen. I will talk about our ammonia cracking technology. I will speak a little bit about LOHC as a carrier material. So I think the presentation that we have heard in the first place fits quite nicely also into our scope. And then I will also talk a little bit about SOFC systems and mainly balance of plant components for this application. Yeah, starting maybe with generating hydrogen. And our company is very much involved in the PEM electrolysis. And here we are a pure play catalyst manufacturer. So the big PEM guys, so companies like Cummins, Plug Power, Nel, Siemens. This would be our type of targeted companies working with us. And here we produce mainly platinum and iridium based for both the anode and the cathode. We have developed a very active material with long lifetime. So we have a lot of durability data generated internally in our application labs, but also externally with institutions and with customers that we have as of today. And one of the important things that has been also mentioned, iridium, for example, the main metal used in electrolysis, is quite expensive, also quite rare. So only 8 metric tons of iridium are available within 1 year of primary supply. If we take it into consideration that this metal also has a very high density, all this 8 metric tons we could put in a very big suitcase. So it's not a lot of physical material. So we need to make very good use of it. And this is why we have developed already 4 generations of different catalysts with particularly different iridium loadings. So thrifting has happened a lot to make that's possible. Yeah, once the hydrogen has been produced through PEM or any other technology, very likely there is a requirement of purification post-electrolysis. And here a deoxygenation reaction can take place when you wanted to purify the hydrogen from the traces of oxygen that might be left within the stream. So here different technologies can be applied. Both platinum-based and also palladium-based technology. Depends a little bit on the cost. So historically, everyone used palladium because it was super cheap. But then through the usage in gasoline engines, mainly the price of palladium surged quite a little bit. So platinum was a little cheaper, and actually, you can easily substitute both metals, I would say, and kind of exchange. And so the cheaper option in the market today is platinum-based versus palladium-based. And these catalysts come in all different shapes and sizes, so in pellet types, in sphere types, in star type, whatever you guys prefer, that's all available. Also, I think one very interesting move that many of the large EPCs are currently making, companies like Linde or Air Liquide, for example, they also look at oxygen as a value stream. And also here in the oxygen, there might be trace amounts of hydrogen. So through a catalytic dehydrogenation, you can also get rid of the hydrogen and build use cases for the oxygen as well. Yeah, and once hydrogen has been produced, has been purified, I also wanted to connect to the former speaker, it needs to be transported. Because I come from Germany, and Germany we have big problems with high energy prices and high energy imports, because we cannot produce a lot of energy by ourselves. So we're really dependent on energy exporting countries like maybe Australia in the future. And yeah, different types of carriers are obviously been discussed in academia for many, many years, but also within the industry. So in Germany, I can tell you we are very much hyped by ammonia. Why? The infrastructure already exists and it just needs to be scaled. And we believe this is the main advantage for ammonia at the current place. Also, when we look at the catalyst space, for example, our company is involved within the ammonia value chain for many, many, many years already. And the main application for us is so-called ammonia oxidation, Ostwald process, mainly the fertilizer industry, or Australia. There's also big markets with companies like Orica have been shown to produce explosives, for example. So yeah, we know a lot about this industry, know a lot about problems with ammonia, and we know a lot how to make best use of it. And so our company has also decided, to move a little bit forward in the value chain. So we have, in partnership with companies, developed technology for ammonia synthesis. And also what we're going to show today in the presentation, we have developed own technology, proprietary technology that we supply to different players within the market for the cracking. And then also one field which I believe, particularly in the maritime space, will have a future, is also the direct combustion of ammonia. And when we look, for example, at the big engine guys, companies like Wärtsilä, for example, in Europe, so they have already concept engines running and demonstrators in the field. And yeah, certain companies might require a little pre-cracking, so they crack maybe 10% of the ammonia and feed a little hydrogen besides the ammonia into the engine. And one of the big problems that comes with ammonia combustion, unfortunately, is N2O. And yeah, N2O needs to be abated, and this is why we have also decided to work more in the field of emission abatement, particularly designing products for N2O abatement. N2O is also a problem for the ammonia oxidation, ultimately, so we already have existing technology that we are just retrofitting to engine-based applications. Yeah, and here, so this is our brand name. It's called Heraeus. It's a ruthenium-based catalyst technology that has been developed for the efficient ammonia reforming or ammonia cracking process. So we are positioning ourselves particularly in the low temperature cracking application, so 450 to 500 C. This is where we will play, while non-ruthenium applications, for example, nickel, I think is very well studied and used by many players, is more high temperature application, and so we see certain difference in the temperature curve between these two different materials. As you can also see, I mean, this catalyst material from many papers has been well characterized and studied. So we have here a sphere type with a very, very thin axial. And also when we look, for example, at the ruthenium distribution, you see that we are somewhere in the median in the 7 nanometer range, which we believe is best for a catalyst that has been developed by our company. Yeah, when we look at ammonia cracking, we basically see different use cases, and different catalyst technology will be applied for these different use cases. So we see 3 in particular. Number 1, large industrial processes. And one could think about, for example, a large harbor where you have ammonia tanks and you have the ammonia tankers providing ammonia into these large storage facilities. And then you have a large scale cracker, and the hydrogen then ultimately is directly fed into the existing natural gas grid. So there are many case studies currently within Europe, for example, in the Netherlands, in Belgium, and also in Germany, where big EPCs have already built their pilot plants. And we also know that, for example, in the Korean market, there are many pilots planned through smart energy institutes, for example, and large companies. So this is for sure something which will find a way in the future. What we realize is that many of these companies, they simply try to retrofit the existing SMR technology. And I think it's quite a smart move because SMR is quite well studied. So the reactor technology is very well known. The equipment is very well known. So it's just a different feed that you feed to the reactor. And also here catalysts are very well studied. And yeah, so I provided, a few examples. For example, this ring-based catalyst, which might have some pressure drop optimized behavior ultimately. Second, in the middle, we also do believe that decentralized application will have a future, and for both synthesis, think about a small windmill somewhere or small solar field, and you just want to store a little bit of the energy that you are producing all over the day, while at the same time also decentralized cracking will have a future. And also same here, for example, in the European market, some examples are with steel mills or other applications that require a lot of energy. They will have a decentralized cracker right on site working with ruthenium and potentially other metals. Big question is here, why ruthenium, for example, might have some advantages. So we believe it's a plug and play. So there's no activation required. For example, like with a nickel material, you would have it. You can have very dynamic reaction conditions, and it will not really harm the catalyst activity. You can stop for a certain time, you can restart, and the catalyst will just survive. So whenever there is requirement for energy supply through ammonia cracking, it's a very, very robust technology that is out there. And then third, I already talked about it a little bit, NH3 also as a fuel. We can think about a pre-cracker, for example, and I also brought a few examples here as product pictures. It can be honeycomb-based technology, it can be knitted wire-based technology in order to generate some turbulence of the fuel. And then also for the N2O abatement, these products quite look similar. So we know it from the classical automotive technology, for example, where you can have an SCR system or a classical three-way catalysis system based on a ceramic or on a metallic monolith. And yeah, as I said, this technology will be retrofitted in our point of view. Then maybe another promising hydrogen carrier. I wanted to mention it because there's a very famous German company working on this technology called Hydrogenius, and also the previous speaker already mentioned that there might be a hydrogenation step and a dehydrogenation step involved. And here you can use platinum and also ruthenium for both. Also, I think it's nowadays very well studied. Kyoto has also been mentioned already in the previous discussion with a nice demonstration. So we also believe this technology is very much reliable already. Maybe there are some questions around cost, but also with the scale, we also believe in this technology. And also, let's say, our opinion as a catalyst manufacturer is there will be not just one dominating technology. We believe that also when we think about methanol or e-methane, every carrier will have its space and its application advantages and disadvantages. So there will be not just one. We believe there will be a variety of different ones. And also when we think about the energy consumption as of today, there is so much that needs to be replaced that we also truly believe from the capacity standpoint that there will be enough space for every single carrier. And then last one, I wanted to mention it because when I looked at the exhibitors here in Korea, I saw a lot of activities also in decentralized reforming applications for decentralized heat and power, for example, and also a lot of different units I saw. And for this type of application, and it can be an SOFC that they are utilizing, it can be something different. Also in the balance of plant, different catalytic components are being applied. We can work a little bit on the saturation of the hydrocarbons that you have been using, because for sure it will not be direct hydrogen that will be injected at the very beginning. For example, in Germany there are discussions to at least feed a little bit of hydrogen into the existing methane that we already have available in the grid as of today, and so gradually there will be a shift. But in order to make use of the methane that we have as of today, reforming, for example, is required. So we have developed nice pre-reforming and also main reforming technology, which can be also integrated directly into the stack through the formulations that have been developed. And then, in many applications, also catalytic afterburner for any potential hydrogen that might be released into the atmosphere might be also required in this system. So I recommend, because I saw 6-7 exhibitors here, very smart concepts, some in the prototyping phase, some are already selling. And so I believe it's quite interesting. And again here, different metals can be applied in different shapes and forms. So it's a little bit depending on the overall engineering setup. Yeah, and also as said, I mean, many companies like our companies, I think we have smart solutions for the catalyst, and also from the commercial standpoint. For example, we have trading offices around the globe which help purchasing people to buy precious metal to the right time, to make it available at the right time, in the right quality, at the right place. But what's super crucial, no technology in the new world will survive without any recyclability. And in my point of view, that's one of the beauty of our products that we have, because they are 100% recyclable. So if you think about iridium in a PEM stack, if you think about platinum in a fuel cell, if you think about ruthenium as the cracking, these metals, they will not disappear. And already as of today, there are very smart collection systems out there, and companies like our company, or for example in China, we have a large joint venture with BASF, BASF, on the recycling. These metals can be reused in infinity. So you might have a first high invest, but then you already use the metal again for new catalyst campaigns, and brings down capex and opex quite dramatically. And the recycling rates, nowadays, because so many materials are very well studied, are super high, in the very high 90% range, depending on the matrix, obviously. But recyclability is one of the big pluses of precious metal related technologies. Yeah, and second very nice advantage, and as I said, our company produces catalysts, we trade the metals, and we also do the recycling, so everything can come out of one hand. But still, as of today, we see that roughly 2/3 of the metals come from primary supply. And the main suppliers as of today, for these metals are Russia, which is not a source anymore. And then second, South Africa, which by far is the biggest provider. For example, when we talk about iridium, ruthenium, platinum, and palladium, it's basically as big as Russia. But what is, of course, also very much known is that it's a very energy-intensive process, ultimately. And with recycling, you can reduce the carbon footprint of the products dramatically. And you see here, figures that have been studied by the International Platinum Group Association in the range of 97%, which I think is also a big plus for secondary metals. Yeah, with that, we also do a lot of research on the metals. So if you want to go on our website, we have just recently published the platinum standard and also the palladium standard, where it's free for download. We do it together with an agency in the UK, which is specialized on this research, where you can read up a little bit about the trends. Also, I said we have a booth here. J63 is the number to remember. If you want to have my contact details, take a photo here of this link. And with that, 감사합니다. And thanks a lot, for visiting the presentation and your interest within our company, Catalyst, and the hydrogen future. Thank you.
Thank you very much. 네, 큰 박수 부탁드립니다. Now, I'd like to have Q&A session, so please wait. 네, 질의응답 시간을 갖도록 하겠습니다. 질문이 있으신 분께서는 손을 들어주시기 바랍니다. Yes.
Thank you for your question already.
Thank you for your speech today. I'm not good at English, but I'll try to deliver my idea in the best way. In the slide 7, you mentioned the industrial process and the decentralized size. I want to know whether there are any difference in the ammonia cracking catalyst in terms of the size of the applying process. For example, kind of the components or the size of the particle or maybe there are some difference in the filling method.
There is, because for large industrial processes, you have to think about of a very large reactor with maybe a few thousand liters. And for decentralized, it might be only 50 liters or 100 liters. So catalyst technology, the formulation of the ruthenium and also other dopants that we add to the material, this will be the same. But the form factor of the catalyst will be very much different, because particularly for pressure drop problems that you will have. So while for a smaller decentralized application, we will think about smaller beads, because you have a lot of ruthenium in your reactor, so a lot of active surface. While for the very large applications, we are thinking more about classical pressure drop optimized carriers, which are also larger in size, maybe with different hole structures. So the technology, the formulation will be the same, but the geometry of the substrate that we are using will be different.
Okay, thank you.
Thank you.
네, 감사합니다. Thank you very much
Thank
for
you.
your answer. And now you may return to your seat.
Perfect. Thank you.
네, 그럼 다음으로 주식회사 삼정 ENC의 매니저이신 정호연 님께서 Advancing Hydrogen Industry Materials, Parts and Equipment Technology라는 주제로 강연을 해 주시겠습니다. 여러분 큰 박수로 맞이해 주시기 바랍니다.
네, 안녕하세요. 네, 안녕하세요. 저는 한국 기업인 삼정 ENC의 정호연 소장이라고 합니다. 우리 삼정 ENC는 그 생산 쪽 분야보다도 좀 활용 쪽에 좀 특화가 돼 있고, 이제 생산 쪽이라든지 이동, 저장 쪽에 이제 발을 뻗고 있는 기업이라고 보시면 되겠고요. 이번 발표에 있어서 수소 산업의 소재, 그리고 부품, 장비에 대한 기술 발전에 대해 이야기 나눠보려 합니다. 네, 저희 회사 소개하고 저희 수소 냉각기, 또 수소가스 제어 시스템에 대해서 설명드리겠습니다. 네, 저희 삼정 ENC는 대한민국에서 지정한 수소 전문 기업으로서 수소 에너지 활용에 수소 산업 발전과 더불어 H2 칠러와 H2 컨트롤 시스템으로 이래 판넬을 제작하고 있어요. 그래서 글로벌 최고의 이제 수소 전문을 이렇게 육성을 하게끔 하고 있고, 또 고객 만족을 위해서 신의와 품질 제일주의 원칙의 혁신으로 이렇게 진정을 하고 있습니다. 네, 저희 삼정 ENC에서 가지고 있는 수소 산업 장비를 만들 때 사용하는 가공 장비들이에요. 머신링 센터라든지 터닝 센터, 또 바이퍼 레이저 등 이러한 아낌없는 투자까지 진행하고 있습니다. 수소 충전소 효율 관리에 대한 내용입니다. 현재 우리 대한민국 수소 충전소들은 기체 수소로 이루어져 있는데요. 근데 이런 충전기의 A사, 칠러의 B사, 그리고 제어 파넬의 C사 이렇게 운영이 되게 되면 운용 비용이 올라간다든지 긴급 보수가 안 된다든지 이러한 부분들이 있는데, 이런 삼정 ENC의 특화된 장비들로 구성이 되게 되면 일원화된 컨택으로 그 업무 부하가 감소가 되게 되고, 또 이제 운영 비용 절감, 그리고 긴급 서비스 이용이 원활하게 진행된다는 장점이 있습니다. 네, 수소 냉각기 부분입니다. 우리 삼정 ENC는 1993년에 창업을 해서 산업용 냉각기로 시작을 했습니다. 그래서 1차 산업부터 최첨단 반도체 산업까지 이런 36,000건의 냉각기의 이런 산업을 보유할 실적이 있는데요. 근데 이렇게 함에 있어서 2017년부터 수소 충전소용 냉각기를 납품, 그리고 H2 칠러 안정화에 성공하면서 현재 대한민국에서 수소 스키드 시스템 보급, 그리고 액화 수소 스키드 시스템까지 개발하고 있는 실정입니다. 수소 냉각기의 기술 발전입니다. 맨 처음 수소 충전소에 이제 구축이 될 때 해외 제품인 그런 부분들을 모방을 하거나 아니면 해외 냉각기를 이렇게 수입해서 의존하던 실정이었는데요. 거기서 우리 삼정 ENC는 독자 개발, 국산화에 성공하여서 국산화율 87% 이상, 또 수소 전문 기업 선정 등으로 지금 현재 독보적인 1위를 달리고 있습니다. 네, 그래프를 더 잘 봐주시면은 맨 첫 번째 드라이 쿨러를 이용한 해외 냉각기가 거의 주력 제품이었는데, 지금 현재 그 대한민국 수소 충전소 상황을 보시게 되면은 수소 충전소용 냉각기는 우리 삼정 ENC에서 독보적으로, 또 상업 운행 중인 대수로는 416대가 있습니다. 네, 수소 충전소의 이제 발전 과정인데요. 지금 현재 이동형 수소 충전소라든지 고정형 수소 충전소, 이러한 부분들에 있어서 모두 대한민국에서는 기체 수소로 이루어져 있어요. 근데 이제 액화 수소를 이제 탱크에 저장을 해서 운송이 가능한 그런 충전소로 탈바꿈을 준비 중에 있어 우리 삼정 ENC도 그러한 기술 개발을 하고 있습니다. 우리 삼정 ENC의 제어 시스템 부분입니다. 제어 시스템이랑 우리 수소 H2 컨트롤 판넬에 있어서 다양한 형태로 수소 생산, 그리고 저장, 이송, 그리고 활용까지에 이르러서 그런 전반적인 수소 제어를 할 수 있는 판넬이라고 보시면 되겠고요. 이번 최근 우리 삼정 ENC에서 블럭 헤더라는 것을 개발하여서 유니온 연결 부위들을 블럭 헤더를 적용함으로써 수소 리크 포인트를 줄인다든지 운용 비용 절감 등의 효과를 누리고 있습니다. 수소 부품 국산화 신기술인데요. 이런 수소 이런 제어 판넬에서 사용되는 이런 부품들이라든지 수소 판넬에 들어가는 부품, 이런 부분에서 우리 삼정 ENC에서 직접 개발하고 생산하고 있습니다. 데칸트 컨트롤 시스템입니다. 데칸트 판넬이란 이 수소 트레일러, 그러니까 튜브 트레일러죠. 거기서 들어오게 되면서 이제 수소 압축기로 이동을 하게 되는데, 거기에서 제어를 할 수 있는 판넬을 데칸트 판넬이라고 부르고 있습니다. 그런 데칸트 판넬에도 우리 삼정 ENC의 블럭 헤더를 적용하여 리크 포인트를 줄이고 또 운영 비용 절감 효과를 누리고 있습니다. 네, 프론트 컨트롤 시스템입니다. 아까 데칸트 판넬 같은 경우에는 튜브 트레일러에서 수소 압축기로 갔다면, 압축을 한 수소 압축기에서 압축한 수소를 이제 저장용 탱크로 이동할 때 사용하는 판넬이라고 보시면 되겠고요. 네, 리어 컨트롤 시스템입니다. 아까 그 압축기에서 압축을 해서 저장용 탱크에 저장을 했으면, 이제 실제로 차량에 충전을 하기 위해서 저장용 탱크에서 수소 충전기로 이동할 수 있도록 제어를 할 수 있는 리어 판넬이라고 보시면 됩니다. 엔드 컨트롤 시스템입니다. 이러한 부분은 질소, 이런 컨트롤이 필요한데요. 수소 충전소에서 이러한 부분에서 질소를 이렇게 제어할 수 있도록 만들어진 판넬이고, 여기에도 계속 모두 블록 헤더가 적용되어서 특허 기술을 적용하였습니다. 네, 우리 삼정 ENC에서는 대한민국의 이런 부품이라든지 충전소에 거의 독보적으로 이렇게 진행이 되고 있고, 거의 대부분 67% 정도 이렇게 상용화되고 있다고 보고 있습니다. 우리 삼정 ENC에서 이제 수소 경제 네트워크를 이렇게 이루고 있는데요. 최근에 이제 뭐 한국가스기술공사라든지 뭐 수소융합 얼라이언스, 이제 수소융합 얼라이언스 쪽에서 저희에게 수소 전문 기업을 이렇게 지정을 해주었고, 또 이런 대기업이라든지 여러 중소기업 등 이런 수소 경제 네트워크를 활성화하는 데 주력하고 있습니다. 우리 삼정 ENC는 기술 혁신과 사회적 책임을 다하는 수소 전문 기업으로 성장할 것을 약속드립니다. 감사합니다.
네, 좋은 강연 감사합니다. 네, 그럼 간단하게 질의응답 시간을 가져보도록 하겠습니다. 네, 질문이 있으신 분께서는 손을 들어주시면 마이크를 전달해 드리도록 하겠습니다. 네, 네, 이쪽으로 마이크 전달해 드리도록 하겠습니다. 잠시만 기다려 주십시오.
네, 안녕하세요. 개발되고 있는 부품에 대해서 사용하기 전에 무조건 더 중요한 게 인증하고
네.
이런 표준화 관련된 부분일 것 같은데요. 개발하고 계시는 뭐 피팅, 밸브류 뭐 여러 가지 부품들에 대해서 인증이나 표준화 관련해서는 어떻게 진행되고 있는지 간략하게 설명 좀 부탁드리겠습니다.
네, 지금 그러한 부분들 같은 경우에서는 해외 인증까지는 현재 진행은 되지 않고 있는데요. 지금 특허 기술까지 이제 들어갔고 그 이후에 이제 검사 부분에서 이제 마무리 단계로 이렇게 진행이 되고 있습니다. 그래서 조금만 있으면은 이번 연도 이제 하반기쯤에 이제 상용화에 성공해서 실제로 상업 운전이 되도록 그렇게 생각을 하고 있습니다. 네.
네, 또 질문 있으시면 전달해 드리도록 하겠습니다. 네, 저희 나라 이런 기술들이 너무나 자랑스러운데요. 그래서 질문들도 많이 있는 것 같습니다.
제어 판넬에 대해서 아까 사업 분야를 말씀해 주셨는데
네.
그 수소 저장이나 이동 말고 수소 생산과 관련된 제어 판넬도 혹시 사업 분야가 있으신지 싶어서.
지금 제가 말씀드렸던 부분은 활용 분야에서 많이 사용했던 거기 때문에 그 생산 쪽에도 우리 제어 판넬이 뭐 필요하다, 뭐 그런 기술적인 부분에서 좀 사용이 가능하다고 저희가 판단을 하고 그런 것도 준비를 준비를 하고 있습니다. 예.
네, 다음 분 전달해 드리도록 하겠습니다.
네, 좋은 강의 감사합니다. 혹시 그 수소 충전소용으로 냉각기 시장은 규모를 현재 어느 정도로 보고 있는지와 향후 어떻게 그 규모가 커질지 예상하고 있는 데이터가 있으신지 질문드립니다.
네, 일단은 대한민국의 수소 충전소가 약 한 200여 군데 있다고 보고 있는데요. 그중에 저희가 충전소로 따지면 154곳 정도 상업 운행 중에 있어요. 그러면 독보적인 1등이라고 좀 자연스럽게 말씀드릴 수가 있을 것 같은데 미래 발전적인 지향을 보게 된다면 액화 수소로 하더라도 그 마이너스 253도에서 다시 기체로 결국에는 내려와서 마이너스 40도에서 마이너스 33도의 수소 충전 온도를 이렇게 계속 유지를 시켜줘야 되기 때문에 좀 미래 지향적으로는 좀 밝다고 생각을 하고 있습니다. 네.
네, 더 이상 질문이 없으시면 네, 한 분 더 계시는데요. 네,
저희 메인 칠러에 이제 마이너스 40도에서 마이너스 33도를 유지를 시켜주려면 좀 저온 냉매를 사용을 해야 돼서 R507A라는 냉매를 사용하고 있어요. 예.
네, 그럼 더 이상 질문 없으신가요? 네, 오늘 너무 적극적으로 질문에 참여해 주신 우리 참가자 여러분들께도 진심으로 감사드리면서 또 고견 쉐어해 주신 우리 안 의원님께 진심으로 감사드립니다. 네, 자리로 돌아가 주시기 바랍니다. 네, 다시 한번 박수 부탁드립니다. 네, 다음은 Dreams of Paving a Way for Future Sustainable Energy라는 주제로 안 매테리얼스의 CEO이신 안호선 님께서 강연을 진행해 주시겠습니다. 네, 무대 위로 모시겠습니다. 여러분 큰 박수로 환영해 주시기 바랍니다.
Hello everyone, my name is HoSeon Ahn. In the AHN Materials, we have the subject, the talking topic is dream of the paving a way for future sustainable energy, like this. This is outline. So AHN Materials is located in Incheon and Songdo. So we are established in 2020, specialist in startup energy. Our mission is development next generation energy using three-dimensional graphene as our source. Sorry. So we have the human resource. My name is HoSeon Ahn as a CEO, and I'm also working in Incheon National University, and I have the Advanced Heat Transfer and Nanotechnology Laboratory. And my company's AHN Materials CTO is Samjung Kim. He is also working in associate professor in Incheon National University as a multi-scale architecture laboratory as the fuel cell. So we have the 2 PhD researchers and 4 master researchers. about us, I will talk the four the I will talk like this. Number one is the development the three-dimensional graphene material, and second is liquid hydrogen storage tank. Third is gas phase hydrogen storage tank using three-dimensional graphene materials. Fourth is hydrogen production tank through the ammonia cracker system. So our milestone is like this. So recently we have developed, we have shown the prototype of the cryos compressed hydrogen system using the three-dimensional graphene. And here is a market and opportunities. As time going, the clean hydrogen market size is growing like this, and South Korea's government funding is also increasing dramatically. So government policies for the development of renewable energy is very fresh and promising to us. And here is the current stage of the hydrogen storage technologies in market. Liquid hydrogen storage and pressurized gas hydrogen storage. That they have both the pure hydrogen storage system, and in the liquid hydrogen storage system has the high storage density, and the pressurized gas hydrogen storage technology has the low energy demand for the conditioning. However, two type of markets has the various disadvantage like this. The most important is the liquid hydrogen storage technology has a require very low temperature storage that as a 20 Kelvin, and the pressurized gas hydrogen storage system require very high pressure. This is wrong. That 100 bar, that's 400 or 700 bar is right. An obstacle to the commercialization due to their unique properties of hydrogen. So we can see the lack of the efficient hydrogen storage technology. So here we have the roadmap development roadmap of the hydrogen storage tank. We have three models. The one is a compressed cryo hydrogen tank, and second is hydrogen storage tank by the graphene material. Third is the liquid hydrogen tank system. Three type of hydrogen tank has a unique system, unique technology, such like we don't have any cryo system for the ultra low temperature. So it means we just use the liquid nitrogen in order to keep and maintain the ultra low temperature, such like the 77 Kelvin. So because we adapted the liquid nitrogen, it means we focus for the only potable type of hydrogen storage system. So here is the simple table for comparison three types of hydrogen tank. One is compressed cryo hydrogen tank. The unique technology, all type of the hydrogen tank has a cryogenic 3-layer or 4-layer tank. It means we have the ultra vacuum vacuum layer and the ultra insulation layer. Second, here is I want to highlight the liquid hydrogen tank and the compressed cryo hydrogen tank, because we make the ultra low temperature using the liquid nitrogen. Liquid nitrogen has a special properties to evaporate faster than the hydrogen. So because it is the natural phenomenon to evaporate because the 77 Celsius, Kelvin is higher than the boiling temperature of the hydrogen. So all type of hydrogen tank, we can estimate the super storage capacity rather than the normal compressed gas hydrogen storage system. So here is a compressed cryo-hydrogen tank. So we have the 3-layer and the geometric design of portable tank is efficient to withstand both normal storage pressure, it means 70 or 80 bar, of most storage materials, and refilling pressure 100 bar as cryogenic temperature. This compressed hydrogen tank also can be used for the 3-dimensional graphene material. Inside here, we can put the 3-dimensional graphene in order to as the absorbent to store hydrogen. I'm sorry. Here is a liquid hydrogen storage tank. Here we adapt the 4-layer because in portable liquid hydrogen storage tank, because we do not have any cryo system, we can make a very light system for system storage tank. However, here is what is the advantage to apply the portable system, the PMFC system. It means we achieve the zero boil off because we drive the liquid nitrogen is boiled faster than the liquid hydrogen. So, and each layer has a vacuum layer. So we need the 4-layer in order to achieve the zero boil off. So, and this third one is the hydrogen storage material as a 3D graphene. This is our own, the original technology of Ahn Materials. So 3D graphene has 2 types. One is wet fabrication and dry fabrication. Wet and dry fabrications, the core technology is come from the thermal and heat transfer mechanism. It is not familiar with the material development the field. This is this unique mechanism is came from the mechanical engineering of such like the heat transfer. So the inside the tank, inside the compressed tank, we try to fill up the 3D graphene as absorbing the material. The hydrogen tank, so with the 3D graphene storage, the test system has showed the very high hydrogen storage capacity rather than some previous research or some studies. So here now we are confirming and checking for reliability and the reproducibility of data. So but recently we have some confidence to show our materials as a hydrogen storage material. So here's the reported in previous research the hydrogen storage uptake amount is maybe the 3 or 4 weight%. However, our materials, the dry type and wet type material showed very higher than some reported material. However, here is a very interesting result here, the right graph. The hydrogen storage materials show its uptake amount regarding to the surface area. But however, our material our material showed even if the surface area is very low, however, the hydrogen storage capacity is very high. It means the graphene, the three-dimensional graphene, it means the 3D, the porous carbon. However, it must made by the flake of graphenes, each flake. So it means I think that it has own dumps and the unique mechanism to store hydrogen rather than the absorbing system absorbing. So we are proving and checking its the performance and capacity, such like using the hydrogen storage capacity verification. So just the discharge test process producer. So this we just save the insert hydrogen into a small cell containing a substance and just discharge, and we measured its volume of hydrogen from the cell. It's a very simple concept. Maybe you guys already learned this concept in the middle school, the scientific experiment class. So from this one, so this because this does not support the movie. I just showed the concept. When we discharge the hydrogen from the three-dimensional graphene, we can measure the discharge the hydrogen like this. So finally, we measure the stored the hydrogen from the graphene. So finally, we can see its data. The stored data is real. However, we still cannot know why it stored so much the hydrogen inside the graphene. I think that we need more time to verify and prove its mechanism. However, I think that the industry, because as a CEO in the industry, I think that the industry can move faster than some scientific field, such like the good example is OLED, because nobody knows why OLED working and operate like this. However, we already see some TV or some display in the industry. So this is our final prototype of the PMFC and the hydrogen tank. Because our goal is a portable type of the hydrogen hydrogen storage system. So using the very light and very light PMFC with the portable hydrogen tank. Regarding to application and require the working time of the drone or the PMFC, so we can apply the various type of the hydrogen tank, such like the cryo compressed hydrogen tank or the liquid hydrogen tank or three-dimensional graphene, the material tank. This is our dream for the future of a hydrogen system for portable. So we just want to use the cartridge concept of the hydrogen. It means here is the drone. Drone needs some replacing cartridge of hydrogen. So here is the swapping or replacing system of hydrogen tank. Just this system is ready to produce the hydrogen cartridge regarding to the store condition. It means if it requires ultra low temperature, this system must keep and maintain its condition. However, automatically the hydrogen cartridge must be replaced to the drone or the portable mobile system. So portable hydrogen production system from ammonia cracker. This is just another our application is on the development in our company. So ammonia global market size also increasing because there are lots of the demands of the hydrogen carriers. So it's the process, the advantage and disadvantage of the ammonia system for carrier, the hydrogen carrier. The ammonia carries the 70% of the hydrogen by weight. However, in volume energy level, so hydrogen has 2 times more than the liquid hydrogen. So ammonia has the very attractive to the hydrogen carrier. So here is we make idea if we combine the ammonia carrier, hydrogen carrier of ammonia and the production system as a portable tank, it means that we can achieve more milder condition to store hydrogen and produce hydrogen. So here is our concept from the thermodynamics and thermal engineering, the pressurized ammonia tank, and reducing the pressure part. Pressure part, we have expansion, not only expansion valve, so we just use a capillary tube. Using the capillary tube, and we just apply restore and regenerate the heat because the ammonia cracker system require very high temperature, so over the 500 Celsius, in order to crack the ammonia. So for using the catalyst, even if you use catalyst. So this cracker system has require two core technology. One is catalyst system. Second is the system. We just complete the design our concept of the portable type ammonia cracker system. Second is Professor Samjung Kim is developing the cracker the catalyst system. So because our background is mechanical engineering, and heat transfer, so we are trying the microchannel and in order to enlarge the surface area for the contact with the catalyst and the ammonias. So we just through the CFD and the simulation result, so we can expect its performance of the crack performance, and the efficiency is also very high. We achieve the 49%. And finally, and we this is it's a design of parts of the ammonia cracker system. And here is this concept original own its concept. It means this system has when the initialization of the ammonia cracker, we use lithium-ion battery. However, when start to operate and when the cracking condition is reached on over the 500 Celsius, then we can guess the stable production of the hydrogen. So then we use the electricity from the PMFC. So here is a very important concept. How can we reduce the electricity, the portion of the produce the electricity from the PMFC? So our target is 10%, only 10%. When we just use, we use the 1 kilowatt PMF system, it means we just need 100 watt to operate the portable ammonia cracker system. So nowadays we just reach 13%. So through the engineering, with the precision approach, in order to reduce the heat loss, so I think that we can achieve the 10% of the electricity usage. So this is the future roadmap from this year until the 2028. We want to show some our goods and make them big market. So Yeah, thank you so much.
감사합니다. 네, 큰 박수 부탁드립니다. 네, 안 머테리얼의 밝은 미래 기대해 보겠습니다.
네,
그럼
감사합니다.
네, 질문 받아보도록 하겠습니다. 질문이 있으시면 자리에서 손을 들어주시기 바랍니다. 네, 마이크 전달해 드리겠습니다.
Hello. Am I understand right that you put graphene in the liquid hydrogen tank and then you're removing the liquid hydrogen? How you ensure that you're not removing graphene?
No, I'm sorry. So you mentioned graphene is for the cryo compressed tank, not liquid.
No, I understand.
Yeah.
But
You
where
don't
do you
understand.
use the graphene, for the hydrogen or for the nitrogen?
For the hydrogen.
Okay. So you put graphene in the tank.
Yeah.
You put liquid hydrogen in the tank.
Yeah.
You store it.
Liquid?
Then
No,
you-
gas type. Gas.
Gas.
Yeah.
Then you're removing it.
Removing?
In gas form, you're removing it from the tank.
Yeah.
Okay. How you ensure that the graphene, which is nanoscale, is not going with the gas?
Because this system has a filter. The filter. It means your concern is when we discharge hydrogen from the tank, the graphene is go on the flow together outside.
But what is the maximum size of the tank you are thinking?
So in our booth, we just realize the prototype is the maximum the volume is 300 milliliter right now.
And what's happening if the graphene goes through your filter? Is it not destroying the fuel cell or where you are using it?
No. Graphene cannot go outside.
Okay.
Yeah, because we use filter and we just check the before and after of the experiments and doing the operation.
Okay, thank you.
Yeah.
네, 감사합니다. 질문 있으신 분 없으시면 다음으로 진행하도록 하겠습니다. 네, 대단히 감사합니다. 자리로 돌아가 주시기 바랍니다. 큰 박수 부탁드립니다. 네, 이제 마지막 강연이 남아 있는데요. 이번 강연은 TUV 라인란드의 완힐미님, 비즈니스 디벨롭먼트 매니저 APAC이신 완힐미님께서 준비해 주셨습니다. 강연 제목은 Process Safety in Hydrogen입니다. Mr. Wan Hilmee, please. 네, 여러분 큰 박수로 맞이해 주시기 바랍니다.
Hi all, thanks for the opportunity to talk today. My name is Wan Hilmee. I am the Business Development Manager from Ristech Solutions, a full subsidiary of TUV Rheinland. We are part of TUV Rheinland since 2014. And I'll be talking about risk management and risk assessment for hydrogen industries, basically. A quick introduction about our company. We are known as Ristech, originally from the UK, back in 2001, and we have several offices all around the world. I'm coming from our Malaysia office, and we have around 260 full-time employees across 16 offices worldwide, and almost more than half of the figure are sitting in our UK offices, 3 in Scotland and the rest are in the UK. And we are around 40 million euro in revenue last year. And we are working with 6 diverse market sectors. And we have delivered thousands of projects with a lot of clients all over the world, mainly for major accident hazard industries. So anything that falls under major accident hazards, we have the ability to assist either the operator or the big contractors. Anyhow, The risk management that I'm going to talk is all about the way how we manage the risk, mainly the high risk, and it may applicable to the big contractors. Potentially in Korea, we have a big contractors, the engineering contractors, the EPC contractors, and also for the facilities owner. For instance, like Shell. I mean, yeah, oil and gas example is like Shell, Saudi Aramco, things like that. And we have several business stream basically. The major one is on the left side, consulting, and we are doing things like hazard identification, things like HAZOP, safety critical element, safety critical equipment identification, and for the same consulting business, we are doing the learning as well. We provide the training to educate the client how to do the risk management, how to manage your risk, and how to reduce the risk basically. And we have some small team in the UK for the resourcing. Some of the client are asking for secondment in their projects. Small inspection entity as well in the UK, and also the R&D. This is our relationship with our parent company. Some of you may be aware that my colleague, Mr. Thomas, from our Germany office, he's our competence leader for hydrogen in TUV Rheinland. And the team members in TUV Rheinland consists of several people. And if you can see Nick Taylor, I think he is sitting in our UK office. He's the representative of Ristec Solutions, but I'm going to talk on behalf of him basically. This is our offices for Ristec only. Yeah, our HQ in Warrington in the UK, and I'm sitting in Kuala Lumpur office. And since TUV Rheinland has bought us, they have global offices all around the world, and it has significantly enhanced our global outreach. For example, if there is any needs in Korea, and the contracting route can be done through local TUV Rheinland Korea entity. And this is some of the industry sectors that we are serving basically, but all of them we are serving in the European region, in Malaysia, in Dubai, in Middle East operation. Mainly we are focusing on the oil and gas and chemical, and hydrogen falls under the clean energy sector. Some of our example client, why we put oil and gas and chemical, because most of the big operators like Shell, BP, ExxonMobil, you name it, they are all going for net carbon zero emission vision by 2050, something like that. So hydrogen is obviously a big thing for the oil and gas operators. And yeah, you can have a look on about the rest of our portfolio. We have more than that basically. This is just a key client for us. Yeah, I'm going to touch a little bit about hydrogen, and I will talk about the risk management, or we call it risk management, the way how we do the risk management and why we are going to do that. As a very brief introduction of hydrogen, yeah, I think all of you may be aware about the properties of hydrogen: lightest element, smallest molecular size. Their leakage rate is higher than any other properties basically. It can permeate through unbroken material. What else? Very low initial energy, invisible flame, stuff like that. So and clearly that from this point, hydrogen can be one of the risk or hazard source basically. And this is the application of hydrogen technologies. I think most of you here are what we call it the hydrogen technologies service provider. So I think you are better than me in terms of the technologies. And the scale of hydrogen opportunities, I think every part of the world at the moment are talking about hydrogen economy. In my country, in Malaysia, we do have similar exhibition as well a few months back, but at smaller scale. This in Korea, the exhibition are way bigger. And I don't have to touch on everything, but as you can see, the hydrogen economy, it covers most of everything. In Europe at the moment, they are talking about to use the hydrogen as one of the energy source to heat up their house, and as a source for cooking as well. In some of other countries, they are talking about to have a transportation system, and all of this will involve safety, will involve risk management. How do you ensure you manage your risk properly? And this is in respect how we are getting ourselves involved with the hydrogen related projects. As you can see from the graph, it go exponentially quite good, basically the growth in terms of the project involvement for our team. Okay, this is the key point of my talk today. How to manage the risk and why we need to manage the risk. Who asks you to manage the risk, basically? So normally in our business, we are getting very much involvement in oil and gas industries. In Malaysia, we have Petronas. In Saudi, they have Saudi Aramco, and they are all self-governed company. So in Malaysia, for instance, Petronas, as a national oil company, they are regulating. They are self-regulated company. So all other operators, in Malaysia, they will follow Petronas guideline. So in a way, our business is very much driven by the regulatory compliance. So, like it or not, the operator or the big contractors, for example, if Samsung or Hyundai or POSCO are bidding for a BG or doing a project in Malaysia, they have to engage a third-party consultant like us to undertake their risk management studies, basically. So our product is a report for certain part. So it always started with the risk identification. You have to identify your risk for your projects. If, for instance, if you are talking about building a new hydrogen plant or something like that, you, as a main contractor, as the owner, you have to identify your risk. So normally for the first part, we will rank the risk either low, medium, or high, something like that. So for the low, normally the project owner, I give you example, maybe Petronas in Malaysia, the low risk will be taken care by themselves. They do have internal management system, HSC management system. They are talking about job task analysis, SOP, standard operating procedure, stuff like that. So Risk-Tech as a company we will not be dealing with the low risk. So like the red hat, wearing what we call it eye protection, stuff like that is not covered by us. It's more on occupational safety. But we are dealing with the high risk. So anything in the risk identification that is identified, we are dealing with the high risk only. Then we will take it further for the more deep studies that will follow. We will follow all the studies will be done in accordance to the international best practice. Some of them are ISO guidelines, some of them are Shell guidelines, some of them Petronas guideline. Even though it's for hydrogen, they will still follow the same guideline, basically. For example, and then after risk identification, we will go for risk analysis. I will show you in next slide what type of studies that we are doing. Some of them require some specialized software, and we do have the internal resources to undertake all those complex process safety engineering studies, basically. And of course, the last part is the risk evaluation. And the idea of risk management is not to eliminate your risk. You cannot eliminate your risk. So for the all high risk identified in the risk identification exercise, you will be what we call it, we will try to reduce the profile of the risk to a region where it called tolerable risk. How to know it's tolerable or not? Again, it depends on the guideline that you are following. So I believe for each country, they do have their own guideline. They will identify their own risk assessment metrics or something like that. So as long as we can reduce the risk to the tolerable risk, so we are meeting the requirement basically. And why do we need to manage? Again, it's a regulatory driven. We have to do it because it's bound by the law basically, for your region, for your country, for any projects that you are dealing with. For instance, in the UK, any hydrogen facilities that handling less than 5 tons, they will not go for detailed risk management. But beyond that, it will fall under COMAH regulation, COMAH in the UK. So if they fall under COMAH regulation, then you have to do extensive, what we call it, risk management studies. And this is another important, just to distinguish our services, risk tech services, mainly on the green part. We don't deal too much on the blue color part because it's occupational safety. As I told you before, it's low risk as per, but even though it's low risk, fatalities still can occur. Don't get me wrong, but it may involve 1 or 2 people or less than 3 or 4 people, something like that. But it always happen. Small scale incident, but it always happen. So our target is mainly here. That's why I'm telling you that risk management is mainly for the big contractors and the facilities owner basically. Because we talk about reputation, we talk about changing the design, and it can impact the entire community basically. And you can see the bullet point down there, some of the major accident hazard industries that occurred in the past. This is not non-hydrogen example. Chernobyl, BP Texas in the US, Piper Alpha, Deepwater Horizon. These all big incidents can be prevented if the process safety part is being taken off properly. For instance, if you see the Deepwater Horizon by BP, it's available in the film basically on Netflix. Killed only 17 people, but the damage to BP, British Petroleum, is around 20 USD billion. And still some of the lawsuit is still ongoing until now. So the reputation, the stock market for BP on that particular day is going down rapidly, very bad, plumb on the stock market. So that's why process safety is a very much important aspect that can be, I mean, all the big disaster, accidents actually can be prevented if the process safety management is being taken care of properly, basically. Some incidents that I managed to get it from the website. For hydrogen, 2019 in Norway, hydrogen fueling station explosion. Oh, South Korea, 2019, hydrogen tank explosion. From that, I think in Korea, from my reading, they got 2 fatalities in that incident. And also in US, 2019, hydrogen blast. So even though hydrogen is a new way, is a way forward for energy, you have to bear in mind the safety is always come first. So if it happens, it can hit your company, it can hit your organization badly, basically. And most of the incidents, if you read the, what we call it, the investigation report, for instance, like the famous one in Japan, Fukushima, nuclear power plant hit by tsunami. But if you read the incident report widely available on the website, it's all preventable. Where you have to follow the international best practice guideline, whether you adhere to the international standards. So this is back to the big and what we call it, it's all back to the higher management of each organization to deal with. Sometimes in certain countries, it's regulated. So I'm not too sure about Korean, what we call it, regulation about the not only in hydrogen but other major accident hazard industry. But I'm sure that there must be some law about what we call it about risk management. Where can we get involved in your projects? Just focus on the bottom one. We can actually get involved with every single project life cycle, conceptual, early stage, FEED or EPC. O&M is by the owner, project owner, either is a petroleum or company or hydrogen-based company, and also for the commissioning. All right, this is the last slide, what we are doing actually. This is some, or maybe not all, the process safety studies that we are doing in-house. Maybe not everything is related to hydrogen, like HAZID, the hazard identification, HAZOP might be applicable. Quantitative risk assessment, fire risk assessment might be applicable. Some recent of our hydrogen experience with some example from various industries. And some outlook in Malaysia as well. We have 2 big projects that have been kicked off, and the main contractors will be from Korea. And yeah, this is the last slide. Hydrogen is here to stay and growing exponentially worldwide, basically. But the early adoption of safety principle is very crucial. So if you have any question, you can just ask me now, or you can just write me an email. I'll be responding to you. Thank you.
네, 감사합니다. Thank you very much. 네. And now let's see if we have questions from the floor. 질문 있으신 분 계신가요? 질문 있으시면 손을 들어주시면 마이크를 전달해 드리도록 하겠습니다. 네, 없으시면 이것으로 강연을 마치도록 하겠습니다. Mr. Wan Hilmee, thanks again, and please return to your seat.
Thank you.
네, 감사합니다. 다시 한번 큰 박수 부탁드립니다. 네, 오늘 강연해 주신 5분의 연사분들과 그리고 적극적인 질문 참여로 강연을 더욱 유익하게 만들어 주신 우리 참가자 여러분들께 다시 한번 깊은 감사의 말씀 전하며 이것으로 테크토크의 마지막 세션을 마치도록 하겠습니다. 끝까지 함께 하셔 자리를 빛내주신 우리 참가자 여러분 대단히 고맙습니다. 사용하신 통역 수신 기능 그대로 자리에 두시고 또 소지하신 물품은 잊지 마시고 챙겨가시기 바랍니다. 모두 조심히 돌아가십시오. 네, 감사합니다.